Okay. Yeah. All right. Hello, everyone. My name is Antons. I have around 6 years experience in machine learning and data science. I did my master's in AI a couple of years ago, and I started as a data analyst, data engineer, then slowly moved to machine learning and blockchain. And the last 2 years or so, I'm mostly involved with large language models and building agents. So right now, I want to share with you the project that I did recently. Here, so in this project, you can build your own GPT-2 grade LLM from scratch using the PyTorch and 2 different text datasets. So one dataset is the Alice in the Wonderland book, which is in the public domain. It's a small dataset with 40,000 tokens, and it's meant to train the model locally on your machine for like proof of concept. And another dataset is English Wikipedia dump, which is already larger. It's 11 GB large, and it's meant for GPUs. So why I want to show this project is because right now there are so many different tools with which you can easily interact with LLMs, like different frameworks like LangChain or Llama Index, and you have different easy nice APIs like the one from OpenAI. So very often AI engineers are like not even aware or don't know much what's happening in the background under the hood. So I think it's like a good exercise to remind yourself of how LLMs work on fundamental level, how they're structured, so you can understand the limitations and how to optimize it. And another aspect why I think it's beneficial to try it out yourself is because you can play around with different parameters, and you can start to have the intuition of how different parameters influence different things. Like, for example, if you increase the number of parameters in the model, but you decrease amount of data, and then you increase, let's say, batch size. So how long the training will be, how much it will cost you, how you can expect the model performance to increase or decrease, and so on and so on. And for example, when you're hearing about different models or you read about them on Hugging Face, for example, you see 1 billion parameter model with 100 billion tokens trained on. Like, is it a lot? Is it not a lot? Is it expensive to build similar yourself, or is it not? So when you do things like building yourself from the scratch, it can give you this intuition. So here, we are going to use like very simple tools. We will use a PyTorch to build and train the network. And yeah, I suggest that at first we run some of these scripts yourself, and we'll have like a quick demo, and I will explain what's going on. And later we will jump into code to see more details of how it is implemented. And yeah, if you have any questions, I will be happy to answer it after we finish. All right, so here's the main repo. And they also wrote like an article or media with more explanations here, in case you want to like read more in details. So the setup is very simple. We just create a new conda environment, and we install all the needed packages. And then you need to have the API token from Hugging Face. It's needed for Wikipedia dataset because we are getting it from Hugging Face. And there are 2 main scripts here. So as I mentioned, we are using 2 different datasets. So one script is for training a model on the Alice in Wonderland dataset, and another script for training a model on Wikipedia dataset. So let's take this smaller dataset and try to train it here locally. So I'm using a MacBook M2 Pro, 32 GB RAM, and it will take around 1 minute to train it. So let me tell you what's going on here. So there are 2 main parts in the code: data preparation and model training. So right here, we just print versions of packages. And here, we basically deal with data preparation. We download the Alice in Wonderland from the web, store it in the text. We chunk the text and shuffle it to split to training and validation data set. And right here, we are using a small model, which has just 256 tokens as an input. And we are using batch size of 8. So that's why we have just the sets of 8 of like eight batches with 256 tokens. And here we calculate approximately how much tokens it is. And yeah, as I mentioned before, it's almost 40,000 tokens for this particular data set. Next thing, what we are doing, we are selecting device. And there are three options for device: CPU, MPS, and CUDA. So CUDA stands for GPUs. CPU is just like your central processor. And the MPS, it's a special like framework that optimized to MacBook M series. So when you train on MPS, it will be slightly faster than if you would train on the CPU. Here is the details of the model. I will talk about it later when we look in the code. And then we start training. So here's the training part. We initialize empty model with random weights. We push it to our device, which is MPS in this case. And here we have 5 epochs where we iterate our training data set. And once in a while, we are testing it on the test code, on the test string. So we are giving it the phrase water is essential for all forms of life because, and we give it to the model to try to like predict next tokens. And as you can see in the beginning, it predicts some gibberish, some like very random things, which is expected because the model just starts to be trained. But you can see closer to the end, it gets a bit better. It's still like far from perfect, far from being able to use it in production, but we kind of can see that it goes in the right direction. It has less like random tokens. It kind of has like distinctive words. So it's kind of the general trend goes where it should go. And yeah, in the end, we plot the figure for like training loss, validation loss. And yeah, the script says the model in the file system, so it can be later reused for like inference in case you need. So this one took us 1.27 minutes here locally on the computer. Now let's check how much it will take us to run the same script on GPU. So I'm using the same like command. And you see it's going quite a bit faster. And if I'm like switching to like stats, we can see the GPU now is like used 97%, 34%. So it's now working. Let's go back to where we are training. Okay, and it already finished training in just like a couple of seconds. So you can see the difference, how much faster it is when you train the model on GPUs. Let me tell you a bit what I use. So I just used Vast AI to rent a GPU. I used a single H100. Before that, I was using A100, which is like roughly in this specific case, like twice slower than H100, but also twice cheaper. Yeah, so here in the article and here on the GitHub page, I mentioned some of the results. They are for A100 GPU. All right, so you can see it's quite faster. What I'm going to do now, I will going to run another script which uses Wikipedia dataset, and it will take a bit more time for it to train. So while it's training, we can just take a look on the code and come back in the very end and see like how it like performs. So here, again, it does similar steps. It downloads the data from Hugging Face, the Wikipedia dataset, and does exactly the same steps that I described earlier. Okay, let's take a look on the code. So as I mentioned, again, there's two main scripts, and they are pretty much similar. They're just using different data source. So there are like three main parts in the script. At first, like different parameters and the constants, and then data preparation and training. So here are different parameters that we can use and play around with, but the main ones is which device you want to use. By default, it will take the most powerful available device like GPU or like MPS, and then in the very end CPU. But if you want to test some specific, you can identify like, okay, you can put that I want to use CPU, for example, or I want to use CUDA. Then number of epochs For smaller data sets, you usually can put like 4, 5, and more. But for Wikipedia dataset, since it's so large, you generally just use like 1 or 2 epochs. For example, OpenAI, when they were training GPT-2 model, they had really big data set. I think they had more than like trillion tokens, and they had only 1 epoch because of the vast amount of data. Then you have batch sizes. So when you're using small model, it has less parameters, so it takes less space on the memory, and you can use more batches. But when you're using larger model with more parameters, it takes more space in memory, so you don't have that much data, not that much like space left on the memory, so you generally use less batches, like 2, 4, or 8. And for small models, batches can be 32 batch, 64 batch, even 128 batch. Subset ratio is basically how much from the whole dataset you're taking, because as I mentioned, Wikipedia dataset is like so large, it's 11 GB. You can take just like 1% or 0.1% to save yourself some time. And then this is the text that we are giving the model once in a while to kind of test it during training, to like keep iterating on this. And here we have like example of models that we are training. We have 2 models here, the one with 124 million parameters and with 355 parameters. You can easily like change those parameters or add another model, but actually, yeah, let me increase just in case. Yeah, the main difference is the context length. So the larger model has like more context length. You can give more tokens as an input. It also has larger dimension for embedding layers, and it has more attention heads in the attention mechanism and more transformer blocks. We will see that later in the code where exactly it's used. And then here starts the main script. Again, I'm not going to spend too much time here because we already saw how it works in the output. But basically, we like import the data set, we tokenize it, we split it into training validation data set, we prepare it into batches, we calculate some like statistics like number of tokens, number of characters, and so on and so on. So basically data preparation. Then we select device. Again, as I mentioned, it will be either GPU, which is like CUDA, or CPU, or MPS for MacBook M1 chips. We can optionally test the model before it's trained if we want some initial statistics, but it's optional. And then we start training. So we create an empty model, and we create optimizer, and then we are training it. There are 2 ways of training, like simple training or advanced training. Advanced training is just you're using learning rate warm-up, Gaussian decay, and gradient clipping. So again, you can play around and see how the model quality changes for different like training strategies. All right, training. I'm not going to spend too much time here. We basically go like in the for loop for epochs, and we feed all the data from the like training, and then we just do like back propagation, and the optimizer is just like changing our params. And finally, let's take a look on the model itself. Again, there's a lot of like theory on it. I'm pretty sure like most of you have read on how transformer architecture is working. But basically, we have our here like GPT model, which has token and positional embedding layers. We have dropout layer, then we have multiple transformer blocks, and then like normalization layer and output layer. And the main part here is the transformer block, which consists of just multi-head attention layer, and then we have some normalization layers and the feed forward with GLU, again some dropout layer. And the main part is the multi-head attention layer right here. So we have our query key and value matrices. And in the PyTorch, how it works, it's basically you need to define forward function, and when you feed the data, it creates the graph, and then it calculates like backpropagation and updates values from this graph. So yeah, as you can see, those are basic PyTorch things like linear layer, dropout layer, embedding layer, and we just describe in forward function how they interact, how attention scores are described, and so on. So yeah, that's it. Let's come back to our what we are generating. You can see it's like here, for example, it's still a bit like random, but it's kind of like starts to make some sense. Like it has some words and maybe some grammar, some phrases that can be coherent. Of course, you need to train way more on larger data set to get something meaningful, but it's a good kind of like the proof of concept. All right, thank you. I think we don't have that much like time for questions, but if anyone has, sure.
I'll ask a question. So first of all, great job.
Thanks.
Second of all, I wanted to ask regarding how would adding a layer of complexity into the GPT, how would that perform? I'm just giving you a guessing. Like how would it enhance it? And if so, if you're adding a larger data set, how would it enhance that as well? So I'm just giving you
yeah. Well, generally, the more things you have, it's the better. Like more parameters, more data, more like training time, it will get better and better. But when I personally was experimenting, so you always have a trade-off. You have limited compute, you have limited time. So for myself, on this example, I found out that it was better to take smaller model with like less parameters, but give it more data, rather than like taking a bit larger model with less data. So that's what I found out. But when I was researching in the literature, after some point, when you have like enough data, it's generally better to take like larger models with like a bit less data because they easier find patterns. But here the examples are like quite small, like 124 million parameters is like very small. So yeah, in this case, yeah, it's better like this.
Yeah, thank you. Any other questions?
Yeah. Vocabulary size? Yeah, vocabulary size, it's actually connected with the tokenizer. So like, LLM, like they cannot take text, they're taking just the token IDs. And it's basically dictionary. It's like how many tokens there are. And this is standard dictionary that was used for GPT-2. And it has like this much tokens. And to train, like to create tokenizer, it's whole different algorithm. This one was a byte pair encoding, and it's basically like splits the word and then checks how like much letters, how often they are next to each other, and it creates vocabulary with like specific algorithm. Yeah.
Take it later. Thanks.
All right. Thank you.